And I'm happy to introduce Yuyan Chen, who will discuss her talk on idealized versus realized measures of access in GIS. And just to remind all speakers, there's a 15-minute talk followed by a 5-minute Q&A. And please, for the audience, if you can type your questions in the chat. Thank you. Go ahead, Yuyan.
Okay. Hi, everyone. Can anyone hear me here?
Maybe a bit louder if you can, but I can hear you.
Okay. So how's the voice right now? Is this okay?
Perfect, thanks.
Okay, thank you. So hi, everyone. My name is Yuyan, and I'm a second-year MA PhD student in Geography Department at UC Santa Barbara. So I'm working at the Spatial Pattern Analysis and Research Lab, and my advisor is Dr. Justin Nelson. So today I'm going to introduce my work about idealized versus realized measures of access in GIS science. So first, let's talk about the background. So in GIS, one of the most common things we measure is the accessibility. So accessibility can be generally defined as the ease with which people can reach their opportunities or services. And GIS measures of access often focuses on the proximity, which can be an idealized representation. So such as a potential exposure of children at school location, optimized landfill site selection for growing urban regions, and job accessibility by transportation modes. So in these traditional measures, we assume the proximity equals to accessibility. However, is this true? Well, the answer would definitely be no. Because considering the example of biking first, the buffer zone does not reflect the real-world back accessibility, because someone who lives near the backline does not mean they have access to the backlines. And besides, for the people who do not have a bike or not able to bike, we should not consider this group of people as potential users to the people of who has access to the bike infrastructure. So now it is a time for us to turn our attention to the realized measures. So the GIS measures that represent realized or actual access need to include data on observed use to be nuanced to reflect the social and economic aspects of access. So our goal is to demonstrate how to measure realized access in GIS and to compare idealized and realized measures of access. So here we do a case study in Santa Barbara County. It looks at the access to bicycling. And we choose 4 among 8 cities in Santa Barbara County for this research because definitely we have enough observations, especially for the realized measures within these areas. So they are City of Santa Maria, City of Lompoc, City of Goleta, and City of Santa Barbara. In order to measure accessibility to bicycling, we need back infrastructure data. So we use the OpenStreetMap data categorized by CAN-BACS. So it's called the Canadian Backway Comfort and Safety Matrix. So this matrix is one of the research work that our team has done before. So it classifies all backlines with 3 different comfort levels. So here you can see on the right image, here's a local street backways, cycle tracks, backpasses are classified as a high comfort backways. And the multi-use passes are classified as a medium comfort backways. And the pending backlines, excuse me, are classified as the low comfort backways. And here is the distribution of the 3 comfort levels backlines categorized by the CAN-BACS. So in Santa Barbara County, we have over 300,000 meters long low comfort backways, about 70,000 meters long medium comfort backways, and about 24,000 meters long like high comfort backways in meters. So here I show this like in 3 different colors. And there are 2 more data sets that they used for this research. So another one for the idealized measures is the census tract population data in census block level. So, and the one we used, excuse me, for the realized measures is the origin and destination data aggregated by Strava. So Strava, which is a physical activity mobile application tracking the user's bicycling records. So here, like as the image shows, so Strava use hexagons to show the patterns. And the key benefit of using hexagons is they tessellate to form a regular continuous grid. So that's a reason that we will aggregate both for the idealized and the realized data to the hexagons patterns later. So another issue may be interested in is, so we do know that Strava is a biased data set because it's a physical like activity application. So however, our team has proven that the commute ridership has been shown to be a strong predictor of all bicycling because the 2 measures are correlated. So Strava, as a crowdsourced fitness app, can offer bicycling data to fill the gap of the official data set. So to measure the idealized access, we create 500-meter buffer zone along all bike lanes and calculated the proportional population within the buffer zone in census block level, so which is a percentage of people that we assume that they have the access to the bike infrastructure, and aggregate this into hexagon patterns that as we introduced before. So the results shows that all these 4 cities do have large portion of population who has accessibility, because the darker blue color shows like this. So here is a question again. So is this true? Well, to answer this question, we need to look at the realized measures right now. So here is a descriptive statistics for the 2022 origins and destination data set from Strava. So including number of Strava users, number of total trips, and number of commuting trips here. And the green color means the number is small, and the red color means the number is large. So at the first glance, it seems like the Goleta has the largest number of all these river rebels. And Santa Barbara is the second largest here. And among the 3 variables, we're gonna choose the commuting trips from our regions to measure realized bicycling access. And here we can see in Santa Barbara and Goleta, the right 2 maps here, there are medium and high volume in the realized measures, and 8 coordinates with a high proportional population in idealized measures. However, in Santa Maria and Lompoc, volumes are pretty low, so we hypothesize that the left areas would have big discrepancies between their idealized and realized measures, and the right areas would have small discrepancies. So now let's move to the comparison part to examine our hypothesis. So the method that we used here is called ordinal ranking. So just in case if you don't know, ordinal ranking is like, so we have the proportional population number listed here and the commuting trips. So we are gonna rank commuting trips from our regions and proportional population in descending order separately. So it will look like this. So for the proportional population 30, it will rank as number 1, as it goes like this. And then we calculate the discrepancy value as realized ranking subtract the idealized ranking. So it means if the discrepancy is above 0, the realized ranking is over idealized ranking. cyclists would like to do more bicycle commuting activities than the network's estimation, and it means there is greater access or more access in this area. And vice versa, if the discrepancy is below zero, the realized ranking is less than the idealized ranking. So the cyclists would not like to do the bicycle commuting activities than the network's estimation, and there is less access in this area. So here is the results. So the results reveal that Santa Barbara and Goleta's ranking discrepancy number shows more access. And the Santa Maria and Lompoc's ranking discrepancy number shows less access, as we guessed before. So we would give a happy face to the right side and a cry face to the left side. Excuse me. And in a more quantitative way, so the average number of ranking differences between idealized and realized bicycle access for Lompoc is negative 232.41, and for the Santa Maria is negative 184.76. Goleta is only 12.89, and Santa Barbara is positive 133 and 67. And we also want to explore the socio-economic influence behind the discrepancy patterns. So here is an overview of one economic factor, the median household income, and one social factor, the Hispanic population percentage. And as a reference, the national median household income in the United States is $580 according to the most recent U.S. Census Bureau current population survey data for 2022. And the Hispanic population of the United States is 19.1% of the total population. So we can see like the cities with less access are accompanied by lower median household income and higher Hispanic population percentage. And the cities with more access is accompanied by a higher median household income and lower Hispanic population percentage. So from the bicycle access perspective, we do observe that there are distinct discrepancies between these two measures of access in our study area. And so for Santa Maria and Lompoc, they shows less access. Goleta, it shows more access, but it's not significant. And for the Santa Barbara, it shows more access. So we would say that Santa Barbara is the best performer among the cities in the Santa Barbara County. And in a more general GIS perspective, so especially as new data on mobility become more widely available, advancing proximity measures of accessibility is required, especially for the equity analysis. So that's conclusions in the end. And a big thanks to our SPAR lab. So these brilliant people give me tons of great suggestions, comments, and a lot of help to this work. And thank you so much for listening, and I'd love to answer questions.
Thank you very much, Yuyan, for your talk. So people, if you have questions, please type them in the chat. And while that happens, I wanted to ask you a question about the differences between Santa Barbara, Goleta, and the other two cities. Do you think the student population also plays a role? Because most users, or a big, I guess, percentage of users in Santa Barbara or Goleta are students, especially from UCSB, I would think.
Yeah, it's a really good question. Thanks for your question. So here for the Strava data set, we didn't include the UCSB students community number here because UCSB it's kind of the political problem. So UCSB has our own, how to say, the land property. So Strava just, all the governments like related things just cannot get the access to the data here. So here we can only analyze like the commuters patterns here.
I see. Interesting. Thank you.
You're welcome.
So any questions? Please type them in the chat. Let's wait a couple more minutes. So would that also affect people commuting from Goleta to campus, for example, at UC Santa Barbara?
No, because let me show this to you. The study area map. So this one here. So the UC Santa Barbara is actually between it's downside of the city of Goleta right here, and you can see it's not showing our study area because both the census tract data and the Strava data sets just didn't excuse me, can't include like the UC Santa Barbara's like the geographical data here.
I see. Thank you for the clarification. I think that there are no questions, but thanks very much again for your talk. So we'll move to the next one. We are going to welcome Achituv Cohen. He will discuss his talk on enhanced simplified street network representation for active transportation modeling using OpenStreetMap data. So please take it away. Are you here with us? I believe you are, maybe. Yeah, there you go. Thank you.
Hi, everyone. Can you see my slides?
Yes.
Yes. Okay, great. So in the next 15 minutes, so before that, I'm Achituv Cohen, also from Lab, together along with the former speaker. And today I'm going to talk about a project I have been working on for the last year, I think, about simplification of OpenStreetMap data into a street network representation with focus on active transportation modeling. So in Lab, we are usually interested in any projects on data-driven project to promote and to encourage active transportation. And the one of our project, we were collaborated with a researcher from Israel and from Italy to suggest walkability index on street level. So for this walkability index, we need, on one hand, street network presentation of many cities around the globe in order to compare between cities and find patterns or unique patterns. And second, we need the street network to be presented as center line. So even if street has many lanes, we need only one representative center line of the given street. So in order to do that, we went to OpenStreetMap data, which is, I think, the best open source tool, which tried to represent our reality as much as it could on a map. And that give us an access to different cities. On the other hand, because of that detailed information, it's really hard to create a clear and well-defined representation or center line representation of the street network. So for example, here in Turin, you can see street called Coyo Corso Golito Farnis, and these streets are actually presented by 5 lanes, each one intended to different user, one for bikes, 2 for bikes, 2 for pedestrian, and 2 for cars, for example. But we need some much simplified version of this area, something like the one on the right side of the slide. So each street is presented by only one polyline. Now, this idea is not only relevant for calculate walkability index for street level, but also for other projects. For example, if we want to know the number of collision of a bicycle or the near miss incident for each segment in a given street, we want to suggest safely exposure cost or grade for each street. So still we need a simple and simple and version of our network. So the objective for this research was to transform the OpenStreetMap data into a street network while preserving the original topology and the connectivity between the original street, and also trying as much as we could to shape to preserve the original shape of the street, of the original street. And since we are interested to deploy it on different cities, so we also try to suggest open source tool so other researchers or other people can use it to their research that focus on active transportation uses. So basically our methodology are composed of 4 main components, and I'm going to speak a little bit about each one of them. They identify multi-lane street and reshape them into a single or center line street are going to be the main ones. So in the preliminary task, we need to pull out the data from OpenStreetMap website or project, and we did it by using the great work of Jeff Boeing, which allow us to write only a few lines of code in order to get the vector representation of the OpenStreetMap network together with the tags, which give more information for each segment or each polyline of the street. Why we need the tags? So basically, the tags help us to filter out polyline which are not considered as a street or are not considered as a street for active transportation user. For example, polylines without name, polylines which are considered a freeway, polylines which present roundabouts, and we need roundabout not as a polylines but as a point. So and all of this information can be pulled out from the tags and allow us to remove this polyline. In addition, we calculate for each polyline its angle. Why we need the angle? So that actually leads us to the next slide or the next component, the objective, which is detect or identify the multi-lane street. So the idea is that multi-lane polylines or polylines can be considered multi-lane street scenario when they have the same name, they have more or less the same angle, and they have more or less, and they are more or less close to each other. So how it be implemented? So we use dbScan, which take a bunch of polylines and group them into classes. So each class has more or less the same angle. And then for each class, we create buffer around each polyline and move the buffer to the right and to the left. And if the buffer intersect other buffer from the same group, that means we have here a case of multi-lane street scenario. For example, class 0 is multi-lane scenario, which is not the case for class 1 and class 2. That means we need to now to reshape the multi-line, the polyline belongs to the class 0 into a center line or one polyline. So that is the next component of converting multi-line streets to single-line street. So in the left side, you can see the original shape line, original polyline, which then we use the same buffer we conducted before and took all of the buffer and united them into one polygon. Now we can start and find the first and the start and the end of the new polyline by looking at or searching among all of the points of the original polyline and find those and the 2 points that are closest to the perimeter of the polygon. That point will define the start and the end of the new polyline, the center line of the street of this group. Now we add more points to this new polyline in order to preserve the shape of the original segment of this street. So here we can see now let's zoom out a bit from street level to patch of area of the street network. And we see the result before and the network before and after these steps. And you can see that many streets that were presented by many polyline, but many lanes are converted into one. But still we have many other problems related to the topology that been changed in result of the changes that's been made before. So, and this is the last component of update network, which means to fix the topology and also replace the roundabout instead of many polylines into one point. I'm not going to go into detail on that part because it's quite technical. So here the final result of this patch of the network. So now let's go a bit more about the result. And in this slide, you can see 9 setting different configuration of city setting, from very simple one in figure A to more complex one in figure I. And you can see that at the beginning where there is no, and before that, the yellow lines, the green lines are the updated network, and the gray one is the original network of OpenStreetMap data. And you can see that when the setting is simple, so there is no change, but then the setting become more complex, so we can see more and more changes. And also we can see that our algorithm is not perfect, not correct, not at least not now. We also run our algorithm on other cities, but before that, let's talk about the validation we made on Turin in Italy. So of all of the streets that were being considered as a multi-lane street, we look manually on 20% of them. You can see the streets that are being conducted manually. And so 51% was successfully simplified, 28% had minor flaws, which means that especially when connected to the intersection. So we found some flaws in this connection to the intersection, and 14% achieved partial success, which means that some part of the street, several parts, one or two part of the street was not simplified as we expected, or the algorithm removed all of the lanes in this section. And then we move to validation on our cities. One in San Francisco. So in San Francisco, we not only compare the data into the original OpenStreetMap data, but we also compare it to data came from the San Francisco data. I think it belongs to the San Francisco municipality, and the success rate of San Francisco is very high. It's like 80%. In Tel Aviv, in Israel, we also made the same. We have a different data source this time from the municipality of Tel Aviv, their GIS website. And here the result the success rate are lower, and also we found 2 streets that are completely we got a wrong result, which means all of the streets was just disappear in the final result, or the algorithm didn't succeed to find the multi-lens scenario and convert them into one-lens scenario. And that's about our results or our validations. And lastly, I want to show you a small implication of this algorithm, and it's just like 1 minute explain the data we use for this implication. So one of the project in one of the bike maps is a project that has been developing in Spar Lab, and allow to people to share their information on biking issues. So for example, safety issues or collision on theft. So you can go to this website and share the information about these kind of things. And we were curious about British Columbia or Victoria to see where people are share information on bicycling issue. So we use the same data, and we see the number, and we in these maps you see the number of reports for each segment based on and attach it to the original OpenStreetMap network and then to the simplified network. It's the same data, but the results are different. We can see in the middle that while in the OpenStreetMap network, all of the streets get or 0 reports or between 1 to 5, in the right side, we can see different results, which means that we have actually area with maybe 15 reports. So that can bring us, that can actually can get us to different conclusion or implication after that. So that's, I want just to conclude this work. So try to present a methodology to transform OpenStreetMap data into street network for active transportation modeling. We also have an open source tool that can be used by others. It's still under development, which means that people can use it, but I guess in order to really use it, they can contact me to explain a bit more before it would be like completely ready. And the methodology we presented with actually improve much more this kind of work of simplified OpenStreetMap data into street network data, but it's not perfect yet. And we hope to continue to work on this to get it to a better to give us a better result. And that's it. All from me today. Thank you very much for your listening.
Thank you. Thanks very much for your presentation. If there are any questions, please type them in the chat. And in the meantime, if you don't mind, if you can maybe copy paste your GitHub link on the chat also, so that everybody has access to it, that would be very useful. Thank you. Are there any questions? Let's try to get a few more minutes to see if anybody has a question. In the meantime, I'm wondering what are the next steps for these work that you just presented?
So it's 2 ways. One is we already know where we have problems based on the validation process. So we need to find the reason for the wrong result. I guess that part of it would be very easy. For example, there are so many thresholds in our algorithms, so we also maybe just need to play with the threshold to get better result. And there are some other parts especially when we talk about complex intersections, which maybe require suggest another methodology or added methodology to give our performance better. And the second one is, of course, to use this idea and try to really calculate a walkability index. But for that, we need more data related to our environment. For example, distance to shops, parking, and so on. All of those things that related to our will to choose one street over the others. And that's the other way, which is more, let's say, less technically, and more research direction. Yeah.
Thank you. I believe there are no questions from the audience, so we can move to our next speaker. We welcome now Jiahua Chen. Jiahua Chen, I'm sorry. I'm sure I'm mispronouncing your name, but I do apologize. She will discuss inequity analysis, bike network connectivity, and safety in Santa Barbara and Goleta.
Okay.
Please take it away. Thank you.
Thank you, Rosanna. All right, hello everyone. Let me just put my screen up. Can you see it?
Yes, thanks.
Okay, cool. All right, so hi everyone. My name is Jiahua Chen. I'm from the Spatial Pattern Analysis and Research Lab in UCSB, and I'm very happy to present you my work on an equity analysis of bike network connectivity and safety in Santa Barbara and Goleta. And my co-author is Dr. Tristan Nelson and Peter Cajun. So bicyclists are very vulnerable. According to studies, they are actually 12 times more likely to get killed than a car occupant for every mile ridden. And among all the bicyclists, there are some that are more vulnerable than the other, like the black bicyclists and also people in the low-income community. To make biking safer, of course, the cities has been around, United States has been trying to put in investment in bike infrastructure and in general increasing accessibility for all. And there's a trend in this investment that instead of just investing in individual bike infrastructure projects, now they're looking into investing in a complete and connected network by filling in gaps in current infrastructure or placing in place more traffic calming measures. So this is believed, like connectivity bike network, is believed to promote both safety and access for people of all age and abilities. However, currently in the literature, most of the paper has been focused in how individual bike infrastructure type has been impacting bike safety. And there's not much of them that's looking at how connected bike network has been impacting bike safety. And there's two aspects of it that's unclear. First, the overall magnitude and the direction of the effect. So whether it's positive or whether it improves safety or whether it actually compromise safety. And then the second piece is that there's no study that examined the social spatial distribution of the effect. So that piece is asking whether, so let's say if there is a beneficial effect, whether this effect is distributed equally or equitably among all different kinds of neighborhoods. So in this study, we're looking forward to construct connectivity indices and look at how it impacts bike safety in general. And then the second piece is that we're going to look at how social demographic variables moderate this effect of connectivity on safety. So to put it in a goal statement, we're trying to quantify the relationship between bike network connectivity and safety and examine how the relationship varies for neighborhoods with different social demographic variables. So here I'm going to use SD for just abbreviation. So before we dive into the model, I'm going to introduce you to my study area. So this is Santa Barbara and Goleta. And the black lines defines the outlines of the block groups in the area, which there's 125 in total in the study, in the area that I'm looking at. And Isla Vista here is the university town and UCSB is adjacent to it. We left out this two big block because it has a very different demography compared to rest of my study area. So we left them out in this study. So to put them all together for methods, I built a negative binomial regression model, which is a very commonly used model in crash or collision studies. And bike crashes is my outcome variable versus connectivity and social demography and other control variables will be put in this model to model bike crashes. So first, let's look at bike crashes. I collected a 5-year period bike crashes in the region, and this is how it looks like. So you can kind of see that. So here is urban area of Santa Barbara. It's in a much darker color than rest of the city. But when we are looking at bike crashes, we also need to take into consideration of the exposure measure. So that means how many people bike there, right? Like if there's only, let's say 5 people bike there, but two get collision versus there's 100 people bike there, but only 2 people get collision, that would be a vastly different indication of safety in that on that road, right? So to take that into account, we took this data from Strava, which is an app that record both commute and recreational bike activities on your phone, and then they provide this kind of open source and aggregated data on how many bike trips happen in each segment in the city. So we took that as a denominator for our bike crashes. So here's the map of bike crashes per 100,000 trips. So that kind of simplified the math a little bit more, and we still see this kind of pattern of like mostly higher crash rates in the urban area or the downtown area in Santa Barbara. So that's the first piece of the story. And now let's look at connectivity. And before we are able to construct connectivity, we need to first define the network that we use. So what is a bike network? The most commonly used definition of a network is bike infrastructure network. So if you look at the map on the right-hand side, that's kind of what the existing bike infrastructure, including painted bike lanes, separated cycle tracks, and also bike boulevards, things like that. But in this study, instead of using that, we use low stress network, which not only take into consideration of presence of infrastructure, it also taken into consideration of vehicle speed limits, number of lanes, presence of parking, and facility width. So we believe that this would be a more comprehensive measurement of where the bikers or the cyclists would use in general in the city. So with that, we are able to construct connectivity finally. So in this paper, we define connectivity as into 2 different indices. So the first one is access. It measures the ease of getting to key destination on the low stress network. And the second piece is coverage, and it measures the ease of flowing across low stress network within the block group. So let's look at the first one. So access is measuring, if you put it like in equation, so it's the number of destination that's accessible by low stress roads divided by all destinations that are within bikeable distance. So if we look at the illustration on the left-hand side, so let's assume that this is a block group, and the purple lines are the high stress roads, while the yellow line are the low stress roads. And the three orange points are the key destinations within the block group. And we are calculating, and with that, we can calculate the access for the central block here, which is the dark blue block. And out of the 3 key destinations, we can kind of see that there's only one that could be accessed by uninterrupted low stress road, while the other has to use part of the routes has to go through high stress roads. So in that sense, there's only 1 out of 3 can be accessed, and this block will be given a point of 50. And the same process is iterated for different block in the block group. And at the end, the block scores are aggregated to a block group level, weighted by population. So just to clarify, this process was done by a NGO called People for Bike. So they provided this kind of block level measurement of access. And what I did was trying to aggregate them to a level that would be able to join with other variables to examine the impact of connectivity. So this is the result after the aggregation. So we kind of see a similar pattern of this connectivity, and this is actually the crash rates that I presented in previous slides. So we kind of see a very closely related pattern of like higher accessibility in the downtown area compared to rest of the city. And the second piece is coverage. This is, I guess, easier to understand in general. So it's calculated by length of low stress roads divided by all roads in the block group. So we kind of got from this graph, I got a core sense of like around 2/3 of the roads are low stress. So it would get a coverage of around 67%. So here's how it looks like for the coverage after the calculation. And just to quickly compare with the access measure, it's actually pretty different. So while the accessibility is higher in downtown area, coverage is actually more it's actually lower in downtown area compared to the rest. So the residential area that the bigger block groups actually has higher coverage than downtown area. So that's connectivity. So it's breakdown into assets and coverage. And I'm now gonna introduce you to my other variables. So the first one is the social demographic variables. Among the 5 variables that I used to test, percentage of Hispanic residents within the block group turned out to be the most important indicator of crashes. So that we use it as a interaction term for the model. And other than that, we include exposure, which is the number of bike trips I just introduced you to. And then we also consider topography and urbanness. So now again, turning back to the equation that we have. So in the actual modeling, I use accessibility and coverage to model to represent connectivity, and I use percentage of Hispanic to represent social demographic variations in these neighborhoods. And now we are ready for the results. So in my results, I figured that access actually has a positive relationship or association with crashes, while coverage has a negative association. And if we look at the interaction term, the effect is actually opposites. So we wonder what that means. And we all know that interaction is very hard to interpret in a continuous scale. So in order to better present the results, or to interpret the result, I break down the percentage Hispanic group into 2 categories. So there is higher Hispanic resident block groups and lower percentage Hispanic block group, and the breaking point is at 42% Hispanic. I took this number because it's at the 75th percentile of my study area. And with that, we're able to make graphs. So this is what it looks like for accessibility and crashes. So you kind of see that with 0 accessibility, the neighborhood that has higher Hispanic resident percentage would have a higher number of crashes to start with. And with increasing accessibility, the crashes increase much faster in higher Hispanic population group than the other. So to put it in words, let's say we increase accessibility from 40 to 60 in 2 different neighborhoods with the same, let's say, average trips. We are actually going to see a 30% increase in crashes in the higher Hispanic group, while the increases in lower Hispanic group will be lower, or there will be less increase in crashes. And the second piece is coverage. So here we kind of see that they both benefits with higher percentage of network coverage, but the higher Hispanic residents group actually benefit less, or the crashes decrease less compared to the others. So again, to put it in words, let's say we increase the coverage from 70 to 90%, we'll see almost half of decrease in the crashes in lower Hispanic group compared to the other neighborhoods. So to put it in context, because when I got this result sitting in front of my computer, I was also very confused. So what I do is that I took out two block group that are pretty adjacent to each other, but vastly different in the percentage of Hispanic in these neighborhoods. And I tried to see how they different in their streets conditions. So on the left side, this is what the intersection or the high stress intersection looks like in this neighborhood with 13% Hispanic. And on the right side, it's the neighborhood with 63% of Hispanic. And it's kind of, so some kind of general sense is that the streets complexity at the neighborhood on the right hand side is slightly more complex. So you can see that it's actually more seems like there's more commercial activities at the right side, and also there's more heavy vehicles using the roads compared to the neighborhood at the left side. And in this study, we wasn't able to include heavy vehicle volumes and also normal vehicle volumes as the variable. I think that would be very interesting to look at, but Santa Barbara doesn't have this data for all the road network, so we wouldn't able to include that. But we think that would be one of the reasons that drive the disparity in the effect that we observe. So imagine that both of this neighborhood and all these 6 intersection doesn't have protection or protected bike path right now. And we can imagine that putting a bike path, or let's say putting the same bike path on the 2 neighborhoods, it might achieve very different impact on safety in general, just because the right side is actually more complex. So with that, I would like to conclude my study. We did observe a contextual effect on bike infrastructure on safety, and I think this highlights the importance of using a geographical approach in equity analysis. And I think the talk from this morning about geospatial or geoequity lenses, I think that also give a lots of kind of I think give me a lot of inspiration to really understand this kind of equity studies in more to understand what's happening behind the scene. And I might dive into more the policy and the history of bike infrastructure in the area, trying to understand or tease out what's causing the inequity. But for now, we think that according to the results from our study, we think government may need to invest more in underserved community than the others to achieve the same improvement on bike safety. And there is some limitation to this study. So first, like I just said, we didn't really understand what's happening behind this disparity, and there's a lot more that we can do. For example, we can potentially do qualitative studies and surveys or questionnaires to understand how bike or cyclists have different experience in different communities to understand what's happening. And the second limitation is that the study area that I'm looking in right now is pretty small. However, this connectivity data set that I leverage is actually a national or even, I think, pan-North American data sets where they have very detailed or fine resolution connectivity data for all the cities in North America. So other researchers can also leverage this data set and also the methods to study bike safety and equity in their own interested area. Lastly, we have to admit that we use Strava trips as the denominator, and this is actually a data set known to be biased towards white middle-aged male, because just in general, more of them using this app. However, we did do literature review to see whether it has a correlation with general pattern, and it turns out that it's actually a pretty okay proxy for the spatial and temporal patterns of actual bicyclists on the ground. So with that, I would like to thank all these amazing people who give me immense amount of help during the course of this study. And I would like to thank you all for listening.
Thank you. Thanks very much for your presentation. We do have a question from the audience, from one of your teammates, I believe. So it says, have you experimented with other models? If you have, could you elaborate on the factors that influence your choice of the model ultimately implemented in your research?
Yes, that's a very good question. So I did do a couple of I would say I did try a couple of different models. I tried the Poisson models, I tried a Poisson model with Bayesian techniques as well, but they all show up as pretty similar patterns on the neighborhood level. So the directions are all the same. It would just, I think the actual number is slightly different. Yeah, and I think for what I saw so far, I felt like sorry, I just blank. I think the models that I used, the negative binomial model, is pretty, I think it met most of the we met most of the assumption of this model. So it turned out to be pretty good in terms of the fit of in terms of model fit. Yep.
Thank you. We have one last question from the audience. It says, I might have missed how you calculate accessibility. Do you assume the center of the block as your origin for reaching the different destinations? In reality, the origins would likely be distributed.
Right. That's actually a very good question. So that's what I kind of like about this data set is that it's actually at a block level. So it's actually not taken, so the origin is not assumed from the central, it's actually assumed from the edge of each block actually. So I think it's making this assumption that people usually starting out from a block, if let's say in the downtown area, people usually there's only accessible roads on the side of the block instead of within the block. So I guess that's what, yeah, I'm not sure if that answers to your question. Oops.
Thank you. I believe you could also exchange maybe messages if you need further clarification. Yeah, thanks very much to all presenters for this session, also all of you who attended. We will be back at 1 p.m. Pacific time, although I believe we are all pretty much in the same time zone. Yeah, so thanks very much for attending and see you all at 1 for more accessibility presentations. Thank you.